Thank you very much for attending this talk. I'm Chema Casanova, and I'm presenting the enhancements to the Raspberry Pi GPU driver stack. I'm a member of the Igalia graphics team. I'm an open source developer. I worked during the last years on the graphic stack of the Raspberry Pi devices, mainly on the Mesa Userspace driver and in the optimization of the desktop experience. I'm representing a team. It's not all my work. That would be impossible. That we're working on the Raspberry Pi GPU driver stack. It's composed by Iago Toral, Alejandro Piñeiro, Juan Antonio Suarez, Mayra Canal, and Christopher Michael. So, well, it was 1 year ago at previous SDC in 2023 that the Raspberry Pi 5 was launched in that October. And at the same time, it was launched a new version of the Raspberry Pi OS. That the main highlight was that the desktop was using Wayland for the first time by default. So with this new hardware, the Raspberry Pi is a new evolution from the previous model of Raspberry Pi 4. It's the new generation using the Broadcom Video Core architecture number 7. It has a higher clock rate than the Raspberry Pi. It allows us to draw up to 8 render targets. That is a requirement to have support for OpenGL Desktop 3.0 and in advance. Has better support for subgroup operations, better instruction level parallelism. And well, at that time, when the hardware was in the market that people could buy it, the drivers in the kernel space and in the user space were already created the merge request and landed at the end of the last year. So, well, the support of the APIs is conformance for OpenGL ES 3.1, and at that moment was Vulkan 1.2, and nowadays is Vulkan 1.3. And we have enabled at that time the support for OpenGL 3.1, but it's not conformant because some missing features. So, well, I have this table to show the different names of the kernel, driver space, user space. From the first generations of Raspberry Pi, from 1 to 3, they use the GPU from Broadcom, the Video Core number 4. And the kernel driver is hosted in the kernel module of DRM BC4 that handles the display and the rendering part of the driver. And on the user space side, we have the BC4 driver that supports OpenGL and OpenGL ES. In the Raspberry Pi 4 and 5, we are in two newer generations, the Video Core 6 and 7, respectively. And in the kernel side, we have the BC4, that is the same display driver that we have for the previous generation, and the B3D, that is the one that is managing the rendering. And on the user space side, now we have two drivers, B3D, that is the one for OpenGL and OpenGL ES, and B3DB, that is the one we use for Vulkan. So, well, what happened after a year? Well, we achieved Vulkan 1.3 conformance last August. It was quite recent. That implied exposing 18 new extensions that some of them implied a lot of work. We started taking advantage of the improvements that the Raspberry Pi 5 has in the instruction set related to subgroup operations. So now we can support both valor, shuffle, relative, and quad operation. And at the same time, we have previously only enabled in the compute states, and now there is support for these operations in the fragment states. And well, there were multiple improvements also in the shader compiler backend. This work also implied, as we shared the backend between the Vulkan and the OpenGL driver, the improvements in both of them. This is the list of the extensions that are recently supported. I would like to highlight the implementation of dynamic rendering that was quite interesting and quite hard to implement, and all the work that we did on subgroups that was quite complex on that. On the other part, on the B3D driver, the one that handles the Igalian driver that handles the OpenGL, OpenGL ES, we enabled 7 new extensions, mainly using more of the capabilities that the Raspberry Pi 5 has. I highlighting one that is a small and simple extension that is texture barrier that allows you to put a point of synchronization when you are rendering. So the textures after this point, you have guaranteed that they have been flashed to the memory, so you can reuse in different places. Because it has improved a lot of the performance that we have perceived in the Raspberry Pi. As I commented before, we cannot support OpenGL 3.1 a conformance version because in Raspberry Pi 4 we don't have support for 8 render targets, but we have in Raspberry Pi 5. That was thing that's solved. Not using too much application, but it's a requirement for the spec. We have not support in the hardware for non-seamless cube math filtering because in OpenGL the hardware is targeted for OpenGL-ES and it only targets the seamless cube math filtering. And we don't have support for the some 16 bits render format targets that are the lunar ones. They are not enabled in the hardware, so we cannot use them. But we support everything else. This has allowed us to. Some applications are going to fail, but now we can run a lot of OpenGL applications that previously were not possible to use that. On the kernel side, we have implemented several things. One of those was announced in last XDC, but this finally landed. This is support of CPU jobs. This has allowed us to avoid stalling in the Userspace driver when we have some features that didn't have support in the hardware. For example, the hardware cannot support getting a timestamp, so we manage that, obtaining the information, installing the driver, waiting for the job to finish, and then doing another submission. But we stop submitting commands to the GPU in that time. So the CPU jobs delegate that work to the kernel that can schedule that job that is going to be managed independently. And the Userspace Mesa driver is going to continue doing the submissions without the stalling driver. This has been available since Linux kernel 6.8 and Mesa 24.0. One interesting features that we have recently enabled in the kernel is the support of the super pages capability. The B3D memory management unit supports 64 kilobytes and 1 megabyte pages. These are called big and super pages. So to manage that, we need to create a continuous area of memory. We need to enable the transparent huge pages support in the kernel. And at the end, we are making, for example, 16 4K pages together. And this can be represented with only one page table entry. This allows us to access a part of the memory to only do one lookup for the page entry instead of doing all that use space in the cache. So it seems to be an interesting need. At the same time, now we thinking about if we are have support for big pages or super pages, we can do a specific optimization in the user space. With the traces we usually work, we have seen a general improvement on 1.33% in just changing the kernel with support of super pages and without super pages. That is interesting, but we have observed that there is not such a low performance improvement, but it's a big boss in some emulation cases. I'm going to show some videos recorded by my colleague Mayra Canal, that she extracted the ROMs from the PS2 physical copy of the games and ran them on the FR PS2 emulator. Don't worry, it takes 5 minutes to play the video. So we are going to see the burnout. On the right side, you are seeing the video without super pages, and on the left side, we see with super pages support. In the left side, it's impossible to play the game, but in the right, we are getting near to the point that it could be playable. At least the frame rate is almost the double from one to the other, just enabling the support in the kernel. The other example I have is the Resident Evil 4, that we can see that on the left, with super pages support, it's more fluid, the transition. And if you are we're checking the frame rate, it's like 60 to 70% of improvement. So this is something that has recently landed in upstream in the Linux kernel, and we are now studying how we can take advantage of that for other things, like increasing the size of the command list to use a big page instead of 4K pages, and this would remove the number of access that we need to do to the page table. We have other smaller improvements that they are also interesting, that we moved the performance counter definition that we have in the kernel and in the user space completely to the kernel space. So now the driver checks the hardware that you have installed, which performance counter has enabled, and deals everything in the kernel. And the other interesting thing is that last year we enabled GPU stats so you can use the generic GPU top application to know how are the usage of the different hardware queues. And now we enable the memory usage, so we can see there in the first column the number of megabytes that is using each of the different applications, because sometimes the people didn't know which was the application running out of CPU memory. And well, now I'm moving to the user space part, where we have been doing some performance improvements focused on this GPU limited scenarios, using big target resolution at full HD. In the case of the Raspberry Pi, full HD is big. And we have analyzed the performance on B3D using several GLS bench traces, and we achieve performance improvement of around 40% in these scenarios. This showcases the difference in performance in the average frame per second from last year, when that is the Mesa version that is installed in the bookworm release of Raspberry Pi OS, and current Mesa that is from 2 days ago. I was getting that collection during the flight to Montreal. And well, you can see that in some cases we get an 80%, and in other cases we get a 10%. But the average is significant, it's at 40%. So then when we did that measure, we tried to understand what change has caused this performance improvement. Because we say, well, that was huge, and we didn't identify something that showcases. This is not general for all traces. For the GFX bench, it happens. For other, we didn't figure out that. And we made a study about different branch points. What was the change of for a year? What was the change of the improvement? So we identified that there was an improvement in before 24.1. We see that this is the percentage of improvement, and it's clear there. We have other improvements over the time, but this is the bigger one. I was pointing to a patch when we were implementing this texture barrier extension for OpenGL, that at the end is implemented usually by just flashing the jobs that have been already the driver working on them. And we identified when we were doing this implementation that our driver was passing all the tests without doing nothing. So that wouldn't make many sense, because probably we were doing more synchronization that was really needed. The driver was being too conservative. So in cases where a job was reading a resource that had been previously written, it was going to flash the job that was doing the reading. But it is not generally something we need to do if we can use the same job as before. So what we did is we don't flash in the case we are doing this, we are submitting to the same job as before. So what happens if we do this? Instead of having two jobs because of that, we are merging all the draw calls in the same job. And we are avoiding loading all the tile buffer and storing the tile buffer for each job. So this makes a significant improvement. So in order to show this in the conference, I just go to main. I reverted the commit that introduces this new behavior, and I get the number of jobs that were submitted by the different traces. On the left, we have the frames per second of the traces, and on the right, we have the number of job submissions, and we can see the number of job submissions by number of frames. No? So we can see, for example, the reduction on the Aztec demo, that is from 80 to 50, is 40%, or is 40% reduction of the total number of job submission, and at the end, we see the cost of this improvement. So just removing that coming from comparing with and without and with the commit, we see that we can now know why we are improving the performance in these traces. Closing with the optimization, we worked also on compiler backend optimization. We managed to, in a year, to reduce the number of instructions with a shared DB set by 4%. We did multiple optimizations. Some of them were related to reducing spillings, others to reduce, in particular, sets of CTS because the traces were the CDDB were not using them. And in general, we see that there is probably around the 20% of the performance improvement we have done in the year was related to shader optimizations at the end. And well, so as I would like to have some space for questions, the next step that we are going to continue to work is mainly on performance, improving both the OpenGL and Vulkan driver. We continue working on the compiler backend that we probably have many things to implement, allowing the scheduling to parallelize more instructions. Work on reducing more load and store operations from the tile buffer, but because we have already identified that we can increase the work on merging draw calls in the same job. Continue working on the kernel space driver performance. And we are already integrating Perfecto for having CPU performance monitoring, and continue working on implementing new OpenGL and Vulkan extensions that are requested mainly by the users of the platform. And that's all. So any questions or comments will be welcome.
Yeah, I just have a comment. You mentioned that you were lacking support for non-seamless cube maps.
Yes.
There is a lowering pass for this in NER, but you might not want to use it. I don't know.
We're thinking on using it. That's the idea. We already know that it's there, but we didn't have still the time to do that lowering to support them. But well, thanks for the comment.
Thank you for the talk, and thank you for all the work. I'm kind of using a lot of that.
Oh.
And one specific question is, how do I use the latest stuff, and does it apply to Raspberry Pi 4?
The latest stuff. Nowadays, the best way of using the latest stuff is just to build Mesa from the upstream and install it on the system. That's the easiest way to use the last.
Upstream mean like the upstream, or like do you have a separate branch?
No, we have the regular Mesa branch that you have upstream. No, you don't need nothing particular. Downstream, there are a couple of commits that are just to do some small optimization for the desktop use case of Raspberry Pi OS that are ready to try to force in some situations to use tiled format or that. There are a couple of commits that we think about some moment to integrate upstream, but as they modify other drivers in Node, with some assumptions, maybe it's not suitable for that.
Got it. So for me, as going to upstream for kernel, like just manually compiling 6.8.
Yes, we are thinking about in this. We are going to release probably soon a new updated version in Raspberry Pi OS, at least with the commits that we identify that provide some performance improvement.
Thank you. And for pages, do I need to do something, or it's like magically happens?
For super pages?
Yeah.
It will happen when we update the kernel downstream. In other cases, you would need to compile a kernel and install it.
So like even like with the right kernel, it will just work.
It will just work because Mesa has some patches to enable that. check if it's available. If it's available, we are going to do some small changes in that.
Got it. I'm very excited. Thank you.
Okay, thank you.
So as for the super pages, like big and super big pages, will they always be used, or are they based on kind of heuristic of the resources?
Well, they are going to be used based on some heuristics on the size of the buffer that you want to do. But in the user space, we are going to modify, for example, for the command list execution buffer. I think about we are going to get a big page if we have support. In other case, we're going to get the normal ones. So there are some optimization that would improve, that would be available. But the general usage is based on the size of the buffers. Okay, thank you. So if no more questions, we can finish on time, I think. Thank you.